Alright, we're going to end the section with a couple of small notes. So the first small note is that remember that beta 1 hat is equal to the sum of xi yi minus n x bar y bar over the sum of xi squared minus n x bar squared. This is equal to the standard deviation of y over the standard deviation of x times r, and r is the sample correlation coefficient. Okay. And another note is a little longer. So now suppose you are given xi, then the true value of y is yi. And we have provided a prediction for y. So we just introduced that our best prediction, which is the least square line, when taken both xi and yi into consideration. So the best prediction given both xi and yi's is yi hat, and this is equal to beta 0 hat plus beta 1 hat xi. So that's the best prediction. We have inputs from both x and y. But what if we only have the values for y? So if you're only given y1, y2 all the way to yn, no x's, just y's, then it's really hard to give a prediction. The best prediction we can do is a blind prediction, which is the best shot is we just guess the average, which is the sum of yi over n. Okay, there's no doubt that the green prediction is almost always better than the red prediction, but now the question is, how much better? Is the green prediction compared to the red prediction? In a different way to phrase this, how much does knowing the value of xi help us predict the value of yi? Right. So imagine, definitely it's better to some extent, but we want to be able to measure how much better the green prediction is better than the red prediction. So let's measure all these things. So the green prediction has errors. So the error for the green prediction is yi minus yi hat, and this is also equal to ei, recall that. And to measure errors, the standard practice is we square all of them and we add them together. So this is called the error sum of squares. And we can also do the same thing for the red prediction. So the red prediction has, we add the square of the differences of yi and y bar. This is called a total sum of square. There's a theorem, we're not going to prove it. The total sum of squares is always greater than or equal to the error sum of squares, which confirms what I said. The green prediction is definitely better than the red prediction to some extent. Okay, so we want to measure how much the green prediction is better than the red prediction, so we take this quantity, which is called the coefficient of determination. So we take the bigger term, the red error in the denominator, and then we take the difference of the red error and the green error on top in the numerator. Okay, so this is called a coefficient of determination, and again, not proving this, but this actually is equal to r squared, and r, remember, is the sample correlation coefficient. Okay. So this links the least square line with the sample correlation coefficient. So let me introduce the third term before we talk more things. So the red term itself is called the total sum of square, and the green term is the error sum of squares, and the difference is called the regression sum of squares. Okay. So there's a relation between R and these errors. So let's look at some extreme cases. If R is 0, which means R squared is 0, well, that means because the correlation is 0, this means xi and yi are uncorrelated. And because r squared is 0, that fraction over there is 0, which means that the red error is equal to the green error. Well, this is the worst scenario possible because we want the red prediction to be, we want the green prediction to be better than the red prediction. But in this case, the green prediction is not better than the red prediction. So this is saying that knowing xi does not help us predict yi at all. And you can kind of figure it out because xi and yi are not correlated. So knowing xi does not help you at all to know anything about yi. So that's the one of the extreme cases. And the other extreme cases is when r is plus minus 1. Remember, r is only between -1 and 1. So if r is plus minus 1, well, this means r squared is 1. And this means xi and yi are perfectly correlated. Perfectly correlated. Which means that this line, this means that the data points lined up perfectly on a straight line. Well, if r squared is equal to 1, if you look at this fraction is between 0 and 1, and if r squared is equal to 1, you solve it. This implies that the green sum is equal to 0. Which means this makes sense because if the data points line up on a straight line perfectly, then yi hat naturally equal to yi. So in this case, knowing xi help us to perfectly predict, because r is equal to plus minus 1, perfectly predict yi. Yep, so that's the two extreme cases. When r is 0, xy. The value of xi does not help you to know anything about the value of yi. If r is plus minus 1, then knowing xi directly implies that we know the exact value of yi. But in most cases, r is between these two values, so the scale goes from 0 to 1. So summary is the larger R square, which is called the coefficient of determination, the larger R square is, the better xi helps us determine the value of yi.